Okay.
Sure? Okay.
That's nice. Question at you. No, sorry. There are foreign students participating from foreign countries, so let me speak in English. Okay, our seminar is on elliptic integrals and elliptic functions. First, actually, in today's mathematics, elliptic functions are defined quite simply. What are elliptic functions? Is just doubly periodic, meromorphic, function on the convex plane. Doubly periodic means there exist two complex numbers which are linearly independent of R, namely they form a parallelogram. And if this function has two periods in the indices, that's it, nothing more. So maybe it seems too simple for you, since you know already probably complex analysis and so on. And in fact, such an object was very important in 19th century, and it gives this theory of elliptic functions was actually a prototype of, for example, today's algebraic geometry, and many it is also related to, for example, number theory and so on. So, although this definition is quite simple, or it has a deep meaning. And but there is no ellipse here in this definition, although it is named elliptic. Where is ellipse? Actually, in 19th century, it was found by, for example, Abel, Jacobi, Gauss, that it is an inverse function of elliptic integrals. And what are elliptic integrals? Elliptic integrals is integral of this kind. here R is a rational function, namely polynomial over polynomial of two variables. And this phi is a polynomial of degree 3 or 4 without multiple roots. But yeah, such details will be discussed later. And yeah, for example, the program of finding the length or arc length of ellipse gives a kind of elliptic integral, and that is the origin of the name of elliptic integrals. So, well, yeah, I think it's not very illuminating name, but that's a traditional name. And yeah, exactly speaking, such an integral defines a function of z here, and as a function of u, this defines an elliptic function in this sense. This was our discovery of Abel, Jacobi, Gauss, and so on.
It doesn't depend on the pass from z0 to z.
Yeah, of course, it depends, but well, yeah. And other parameters here. But we consider it as a function of z, and of course, actually, it is a multi-valued function, actually. So we have to make the meaning of inverse function clear, but it will be done later. And yeah, so actually, there are many subtle points in this integral, because we have square root. So where does this square root, where is this square root defined, is already a problem, namely which sign should we take, and so on.
Must have positive.
If it is real and the phi is real and so on,
It's real or positive?
yeah, in that case, maybe okay, but if you go around some contour, then sign might change. For example, as you know, if you go around a circle around 0, this square root of z changes its sign. So what should we do with this changing of sign?
Choose a branch.
Yeah, exactly. So we have to consider Riemann surface, about which I shall explain later in detail. And so since this is a multi-value function, we should construct a Riemann surface, and actually we have to compactify this Riemann surface later, which gives a torus. This is analogous situation is like this. Well, if we compactify complex plane, then we have the Riemann sphere. This procedure is analog of this compactification. And as you know, such a torus can be identified with complex plane or factorized by some lattice. And here we have to choose periods, and actually we can choose these periods as this, namely integral around a cycle on this compactification of Riemann surface of this function. Actually, this is what Abel and Jacobi found. Actually, Abel-Jacobi theorem is more general theory for algebraic surface, algebraic curve. But in this case, Abel-Jacobi theorem reduces to this identification, isomorphism between this compactification of the Riemann surface and this construction of torus. That will be discussed probably in November, I guess. So that's how elliptic functions and elliptic curves are related. So this omega 1 and this omega 2 are those periods which I used in defining elliptic functions. That's how elliptic integrals and functions are defined. And then what should we do? We should study properties of them, especially properties of elliptic functions. Well, I assume that you know rational functions very well. So elliptic functions are, as I told you, meromorphic functions on vectors in this sense. On the other hand, rational functions can be defined as meromorphic functions on the Riemann sphere. So if you know algebraic geometry already, this is genus 0 case, this is genus 1 case. So both are meromorphic functions on compact algebraic compact Riemann surface. And rational functions are usually defined as fractions of polynomials. Elliptic functions can be represented in a similar way. Now, instead of polynomials, we have to use some functions which are called theta functions. What are polynomials? Polynomial is a very good holomorphic entire function on the complex plane. Theta functions are also entire functions, but of course they are somewhat different. But anyway, rational elliptic functions are expressed as a ratio of entire functions, like rational functions. That's a similarity of rational functions and elliptic functions. On the other hand, yeah, so what functions do you know well? Probably you know rational functions from those school days, right? And there are another kind of functions which you know very well. Trigonometric functions. And actually, elliptic functions have some similarity with trigonometric functions, like this. So, yeah. For example, sine has an addition form. X cosine y plus sine there is an elliptic function called Sn with that I. This also has an addition form. In principle, it's similar, but much more complicated. Instead of cosine, there is a function Cn and Dn. Yeah, I shall explain about those functions later. And with some denominator. Although, of course, this is not very simple, but what is important is that such a value of function can be represented algebraically by those elliptic functions. That's an important property. Pardon? Actually, S n depends on parameter k. Yeah, usually this is fixed, and so I omitted. And actually, we can show, yeah, in this course, there is no time to prove this, but in some sense, having an algebraic addition formula is equivalent that f is an elliptic function or trigonometric function or rational function. So this is proved. In 19th century, but yeah, so actually trigonometric functions can be obtained from elliptic function by some degeneration. When k goes to 0, this parameter goes to 0, elliptic function, for example, Sn tends to sine and so on. But such properties, details will be discussed next week, next week, and so on. Another similarity of elliptic functions and determinant functions is differential equation. For example, sine derivative of sine is cosine. So such differential equation holds. Namely, sine, this trigonometric function, is a solution of this algebraic differential equation. Correspondingly, this analog of sine, elliptic analog of sine, satisfies this is it. Of course not. So here another factor appears. But anyway, such a square of derivative is expressed as a polynomial of the unknown function. But there is another famous, important elliptic function, which is called Weierstrass function, Weierstrass P function. And this function satisfies such a differential equation. Okay, actually, I said that this polynomial in the elliptic function has degree 3 or 4, right? And this polynomial corresponds to the right-hand side of these differential equations.
I have a question.
Yes?
Where do we solve this equation? On torus or?
Oh, yes, on see. Actually, it has
And
it's a
can
point.
this solution understand and be expressed through the ordinary functions in some coordinates?
What do you mean by ordinary functions? That's a very, deep, actually it's a deep question. Sn cannot be expressed in terms of elementary functions in the sense that it's a finite combination of polynomials, trigonometric or exponential functions, local, and their inverse functions and so on. Yeah, there is such a theorem. So it's a real new function. Or maybe it's worth recalling. Arcsine is this one. And the inverse function of Sn is And this comes from and this differential equations is equivalent to this expression of impulse function. In this way, differential equations and elliptic integrals are related. Okay, so those things will be discussed, explained in this seminar. But actually, elliptic function, elliptic integrals are related to many things, too many things that I cannot touch everything. So, other topics which I cannot discuss details in this course. For example, something like this. For example, algebraic geometry and number theory. So the image of this mapping satisfies as we saw this algebraic equation. Or, for example, G2 and G3 are some constants which I do not define here. So the image of such mappings are algebraic terms. In situ. And since we have periodicity, torus is embedded into seat. So with compactification, and then we have to put infinity. Anyway, so we have such an embedding. Well, yeah, we have to modify C2 somehow. Like, yeah. It's such details will be discussed probably in October. And since this on this torus, these elliptic functions, such a torus is called elliptic curve. Curve because it's one-dimensional over C, although it's our surface as a real manifold. So algebraically, this is elliptic curve. So we need compactification. Well, in algebraic geometry, it's completion. But so in this way, we have some algebraic description of such elliptic curve, and at this stage, we don't have to use C. Well, actually, we can use any number, any field, and we may use any polynomial with coefficients in this field. And in algebraic geometry, elliptic curves are defined by this form. Completion of such variety defined by this equation is an elliptic curve in algebraic geometry. And for example, in cryptography, K is a number field, some number field, and elliptic curves are defined solely in this way. Okay, this is one connection with algebraic geometry. Another connection with algebraic geometry is the moduli problem. So yeah, let's return to this definition of elliptic curve. Actually, we can choose other periods to define the same elliptic curve. When? Well, there is a strict criterion for this. This is to these two expressions give the same elliptic curve when there exist integers whose determinant is invertible, plus or minus 1. So this ratio is often denoted by tau, and this means that tau is equal to A plus B tau. So namely it's an integral by a fractional linear transformation. And maybe you have seen. Okay, and well, let's assume that the imaginary this ratio lives on the upper half. If this is negative, then we can change omega 1 and omega 2, and this ratio lives in the upper half plane. So this is not a necessary condition. In this case, we can choose plus 1 here. So we have tau in the upper half plane, and sometimes two taus give the same elliptic curve. And factorizing by this operation we have. Maybe you have seen such a picture in some book. Yeah, we can choose the representative of this tau from this region. This is called the modular space of elliptic curve. So this region parameterized is the family of elliptic curves. And in general, in algebraic geometry, some same kind of algebraic varieties appear with parameters, and to determine their uniform single-valued parameterization is a very important and sometimes difficult problem. That's called moduli problem. So, I shall not touch these, for example, modular programs or algebraic elliptic curves. But well, yeah, at least they are related to what I'm going to talk about. So assume that we know what are elliptic functions. And the next question might be, are they useful? And answer, yes. There are many applications in physics and in mathematics. For example, first, let's speak of several applications in physics. Probably the most famous application of elliptic functions in physics is the description of the motion of pendulum. When this amplitude, the maximum amplitudes are small, then our equation of motion is essentially linear. And probably you have heard in the course of differential equation that such a linear differential equation can be solved in general in this way. It's a trigonometric function, and this coefficient gives the period. Actually, this equation of motion is an approximation of real situation. I shall now explain this later, but the real differential equation for this system is this. Not phi itself, but sine phi. But when this argument is small, sine can be approximated by phi. So yeah, we can use this. But in reality, this system obeys such a non-linear, which means that here it is not a linear function, non-linear differential equation. And in this case, phi is expressed in terms of an elliptic function, Sn. Another interesting problem is, yeah, this is not. So, okay, it's not straight. Okay. So do you know what yeah, when this string is yeah, soft enough, then there is some curve. And what is this curve?
Bulk.
What?
I know Russian.
Not cycle. Process, simpler. Exactly. But when it's rotating, what is the function? This is also this is actually Sn. So if you want a graph of Sn function, then you can take a picture of this and that's it. Or yeah, when you solve the motion of solid body with axis, you have to use elliptic functions. And yeah, in many branches of physics or elliptic functions appear. And actually, I'm studying mathematical physics, and I encountered elliptic functions in their branch of mathematical physics called integrable systems. So usually physical system is described by nonlinear equation, and nonlinear differential equation nonlinear differential equations are usually not solvable. But in some very special but very important cases, they have explicit solutions like this, and often our elliptic functions appear. So and that's how I encountered elliptic functions, and now we're using elliptic functions in research too. So yeah, if you know elliptic functions, then yeah, you can for example, use them as examples of solutions of such physical systems. Well, to explain physics, there are many prerequisites. So yeah, probably I shall explain this, but not more. There are some applications of elliptic functions to mathematics too. well, actually Gauss found that arithmetic geometric mean of two numbers are expressed in terms of elliptic intervals. Do you know what arithmetic geometric mean is?
Yeah, we take two numbers and we compute its arithmetic mean and geometric mean.
Right.
Then we take these two numbers and compute
Yeah.
means and so on.
Arithmetic mean and geometric mean. And we can define such a sequence, and then it's easy to prove that they converge to one and the same value, which is called arithmetic geometric mean. And Gauss computed many arithmetic geometric mean of concrete numbers. For example, there are many examples in his collected works. And first conjectured such a relation. And actually, from this is one of the origin, not all, but one of the origin of theory of elliptic functions. Almost at the same time, well, Abel and Ruffini and Galois proved that algebraic equation has a formula of solution using arithmetic operation and roots only when n is no more than 5, right? Yes. But later, Schmidt found formula for quintic equation. Of course, this theorem prohibits such a formula, but if we use elliptic function, then you can write down. Well, I don't want to write down because it's a huge, but anyway, there exists a solution formula for the pointing equation. How about higher degree equation is a good question, and actually there is a formula, but with some much more transcendental functions. Okay, so yeah, I cannot touch upon this point, but the time of this course is like this. First, we start real elliptic integrals and the real elliptic functions. And later, we shall complexify everything. So first, elliptic integrals over R. For example, as I told you, outer length of and then this, or the motion of pendulum, and we can classify elliptic integrals into three categories. Elliptic integrals of the first kind, second kind, and the third kind. Yeah, I think I can prove that in October. And as I told you, by inverting everything. We can define elliptic function. Yeah, probably, we shall study so-called Jacobi's functions. Yeah, Sn, Cn, and Dn. And discuss properties of these functions. Then we are going to discuss complex elliptic integrals and elliptic functions, but first, as I told you, we have to use Riemann surfaces of algebraic functions. Not general Riemann surfaces and not general algebraic functions, but probably we shall discuss the simplest non-trivial case, a little bit more complicated case, and then what is necessary for elliptic integrals. And compactification namely elliptic curves. And then we can define elliptic integrals over C. And using this elliptic integrals, we can prove Abel-Jacobi theorem, which states that this compactification of Riemann surface of this algebraic function is isomorphic to such construction. Therefore, we can use elliptic functions on such varieties and on such torus. And from this description, we can define elliptic functions as W-periodic meromorphic functions. And from this definition, we can prove many important properties. So far, we have only Jacobi's function as examples of elliptic function, but here we shall construct Weierstrass P function, which is interesting, important example of an elliptic function, but not only that, it's a very important tool for the theory of elliptic functions. And we define theta functions, and using that we can define those Jacobi's function as a ratio of these theta functions. So, yes, as a complex elliptic function, this definition is more natural than this inversion of elliptic integrals. But anyway, they are the same, which I shall mention. And probably this is all what we can. And about the variation. From time to time, not every time, but sometimes I shall give you homeworks, and please solve them, and it will be the base of evaluation. And any questions? Okay. Yeah, somebody is on the YouTube, but yeah, no question. Yes?
All the derivation is based on homeworks. There will be no exam. Or will be?
No exam.
So the formula is just the average of all the homeworks.
Pardon?
What
The grading formula.
grading formula?
Yeah, grading formula is just, well, yeah. Max is 10, right? Max, no, not max, minimum 10 and your points or homeworks, you over max points times 50. So if you solve 2/3 of problems perfectly, then you will get 10. Is that correct? Yeah, I think so. Arithmetic is very difficult. Сегодня все. That's it today.
Thank you.
Yeah.